everybody. In this set of video lectures, we're going to look at section 2.7, which covers inverse functions. In math, there are lots of different kinds of inverses. An inverse is just a sort of opposite or something that undoes like another operation. So for instance, as just some examples, the numbers 2 and 1/2 are what we call multiplicative inverses. You probably hear them more often as reciprocals, but they're a kind of inverse because they are opposites. They undo each other. So if we have the numbers 2 and 1/2 and we're multiplying, right, we get the number 1. So that number 1 in multiplication is great because we multiply with 1, it doesn't change anything, or we divide with 1, it doesn't change anything. So that's one example of an inverse. The numbers 6 and -6 are additive inverses. Again, you often hear them as opposites, but they are a type of inverse because they undo each other. So 6 plus -6 is 0. And again, with addition, adding 0 doesn't change anything. So it's a nice property there as well. So inverses are just operations or examples or numbers, depending on what we're talking about, that undo each other. And we also have inverse functions. So inverse functions also undo each other and kind of cancel each other out, just like our other two examples do, right? 2 and 1/2 cancel each other in a multiplication way. 6 and -6 cancel each other in an addition way. Inverse functions cancel out each other, and they do it through composition. So when we compose two inverse functions, they cancel each other out, and we're left with just x as our final answer. And you have this formal definition right here. So let's say you have two functions f and g. If you compose them and you do f of g of x and you get x, and it works the other way too, so it has to work in both directions. G of f of x equals x. Then these are inverse functions. And actually that works here as well. So we're talking about inverses here, just as other examples, right? When we multiply 2 times 1/2, again, we get that canceling idea from multiplication. You get 1. Or if we do 1/2 first, it doesn't matter. We still get the value 1. When I'm looking at my additive inverses, if I add them together, I get 0. And again, it doesn't matter the order in which I add them, I still get 0. So in addition sense, they cancel each other out, again, because 0 is that identity there. So for functions, you have to make sure the composition cancels in both directions as well. If you do know that something is an inverse, we change the notation. So instead of writing G, we write it in this notation, and that -1 is read as F inverse. So that -1 means an inverse. And whatever symbol is here is the function we're talking about. So if you have F, you would write F inverse to mean that exact function's opposite. This does not mean that we're raising anything to the -1 power. If you know your negative exponent rules, it doesn't need to flip or do anything like that. It's just notation. So remember with functions, it gets a little bit weird because it's just notation. You have to remember that you're not actually doing an operation there. And you can write it like this. So we compose our two functions, we get x. And again, it doesn't matter which way you compose them, you still get x. Now, the really cool thing about inverses is that they really are opposites. So what you're going to notice is that, for instance, if you have a point xy that is on the graph of f, then on the graph of f inverse, you have the point yx. So they perfectly flip. So for example, let's say you knew the point 3,4 was on the graph of f, then the point 4,3 is on the graph of its inverse. And this is really helpful because if you know one graph, then you know the other graph as well, because you can just flip all those points and graph that new function. It also tells us about the domain and range. Okay. So the other thing that we know, because of this whole flipping kind of opposite idea, is that the domain of the function is equal to the range of the inverse function. And the range of the function is equal to the domain of the inverse function. Okay, so just kind of making some really important notes here. Your book kind of glosses over this. They don't have a big to do about it yet, but it actually is really, really important. This is a huge help when we're graphing or we're trying to find domain and range. Often it's easier to find the domain of things rather than the range. The range, you really have to see a graph to figure that out many times. So if we can find the domain of our regular function and the domain of our inverse function, then we already have both ranges as well. So you can usually do the domain using just the equation example without having to graph. But the range gets a lot trickier with an equation. So it's really nice that we have this, because if we can find both domains, then I also know both ranges. I don't have to do everything twice. And we'll come back to this a little bit later too as well. All right, so let's do an example. Let's show that each function is an inverse of the other. So to do this, what you need to show is you need to show that f of g of x equals x and g of f of x equals x. So we're bringing in our composition here. Here are our two functions. So I'll just start with this one first. So f is the outside function here. G of x is the inside function in this case. So the outside function is what we start with. We start with that 3x plus 2. And then remember, you're going to take that x and you're going to replace it with the g. So I have 3 times, and my g function is x minus 2 over 3 plus 2. Notice here that 3 over 3 is going to cancel. So I'm left with x minus 2 plus 2, and then my 2's also cancel, and I'm left with just x. So that first one checks out. And now I do the other one. Here, my g is my outside function, and my f is my inside function. Remember, you always start with your outside function. So I'm going to start with the x minus 2 over 3, and then I'm going to replace anything with an x, in this case with the f function. So my f function is 3x plus 2. So this is going to become 3x plus 2 for right here. Then I have a minus 2 over 3. Now I don't really need the parentheses here. It's just 3x plus 2 minus 2 over 3. Here, 2 minus 2 is 0. So I end up with 3x over 3. And then those 2 3's cancel. And I have just x. So because both compositions give us just the x value back out, we do have inverses here. So these are inverses of each other. So if we want to, we can write this as f of x equals 3x plus 2, and f inverse of x is equal to x minus 2 over 3. We do often rename it just so that, we kind of telling the world like, hey, these are inverses. So we give it that special notation there to say that these two are inverses of each other. So they basically undo each other. One thing I do want to note here is you do want to be careful with your simplifying. It does matter the order in which you cancel things. So here, because I have parentheses and I'm multiplying that whole group by 3, I canceled the 3's first because they were right there. 3 over 3 becomes 1. And then I have the minus 2 and the plus 2 cancel. Here, I can't cancel the 3's first because the 3 is over everything here. So it's also over the 2 and the minus 2. So in this case, you have to do the 2 and the minus 2 first, and then you're able to cancel the 3's. So just be careful. You want to make sure that you're simplifying in the right way and not just kind of haphazardly going through and canceling things that look like they should cancel out. I'm sure there'll be some examples that look like they may be inverses, but they're not. So you want to just be really careful with your canceling there and making sure that you're simplifying nice and slowly and checking your work. Okay. Now, it's nice to be able to check that we have inverses, but obviously we want a more systematic way. We don't just want to be guessing at what the inverse of a function is. So there is a way that you can find your functions, your inverse functions, by following these steps. So the first thing we typically do is we typically replace f of x with y. Remember that f of x and y are the same thing. It's just notation. So it's often easier to solve things with y. It's just easier to write. So we usually replace that first. And then what we do is we swap the x and the y variable in the problem. We then solve for y, and one of two things is going to happen. If when solving for y, we find that y is not a function, then we stop and there is no inverse. If we do find that y is a function, then we're done and we have the final answer, and we replace the y with our inverse notation. And of course, you can always check. I'm not going to do all the checks here, You can try it at home, but you can always check the result by doing what I just did on the previous page. So if you perform both compositions and they both come out to be x, then you do know you actually do have the inverse functions there. All right. So let's go through the steps. So here's our function. We want to find the inverse. So my first step is I'm just going to rewrite it. Instead of using f, I'm going to use y, only because it's easier to work with when solving. And then what you do next is you actually swap the y and the x. So you're just going to swap them. So it's going to be x equals 7y minus 5 instead. And then now you're going to solve for y. So here I'm going to go ahead and, let me just rewrite this, add 5 to both sides. I have x plus 5 equals 7y, and then I divide both sides by 7. So I have y equals x plus 5 over 7. Now this is a function. If you're not sure, you can always graph it and check with the vertical line test that we've learned about before. The big thing we talked about with equation form is that as long as you don't have like a plus or minus there, so then you should be fine. So here, as long as you get only one output for all of your inputs, then you do have a function. But again, if you're ever not sure, graph it, and then you can check with the vertical line test that you do have a function. Okay, so this is a function. And then what we're going to do is just replace the notation. So I guess this is still step 3 with the function notation. So f of f inverse is equal to x plus 5 over 7. Do notice that we have opposite things here. So look at your original function. You have multiplication and subtraction. And notice in my inverse how I have addition and division. So it makes sense. These are opposites. So they're going to undo each other. Here you see multiplication and subtraction. Here you see addition and division. So you still want to go through the steps so you have everything in the correct spots. But it's kind of just a nice check at the end to make sure that it makes sense, right? This makes sense that we would have opposite operations here as well. Let's do another example. So we're going to find the inverse. And again, the first thing I'm going to do is I'm just going to rewrite it. Instead of writing f, I'm going to write it as y, simply because it's just easier to work with. And then the next thing you're going to do is you're going to swap. So this becomes x equals y cubed plus 1. And now your third step is we're going to go ahead and we're going to solve for y. So you want to get the y part by itself. I'm going to start by subtracting 1 to both sides. Now I have a y cubed. The opposite of a cube is a cube root. So what I can do here next is I can take that cubed root of both sides. And I have y equals the cubed root of x minus 1. Now this is a function. So when we're taking roots, remember that if it's an odd power, like a cube root or a 5th root or a 7th root, we don't need to do any plus or minus there. If you are taking a square root or a 4th root or a 6th root, then remember we have that plus or minus addition piece that we have to add in. So we learned about this a few units ago or a few sections ago. But with cubes, there's no issue there. So this is a function, and we're going to get f inverse of x then is equal to the cubed root of x minus 1. Okay. And again, just look at the two problems. Here you're cubing and you're adding. Here you're subtracting and you're taking a cubed root. So you have total opposite operations there. All right, let's do 2 more. So here I am going to go ahead and first of all, just rewrite this. Y equals x plus 2 over x minus 3, and then our x value is not equal to 3. So notice here your x value is not 3. That's because 3 would make the denominator 0. So we do have to exclude that from the domain. And then your second step is you're going to swap. So wherever you see x's, you're going to replace them with y's and vice versa. Now, the other interesting thing is you also can swap if you have restrictions. So this x here also gets swapped, and the y cannot equal 3 in this case, right? Because then the y would make the denominator 0. So you can swap those values or those variables in the domain as well. So I'm going to make that change over here too. All right, and now I have to solve for y. So this one's a little bit trickier. So we want to think how we can solve. What I can do here is I can use a cross multiplying technique, or you can think of it more like a fraction. Let me give myself a little space here. And think about, well, how do I cancel that denominator? And I can multiply both sides by that y minus 3. And keep in mind, these are in groups. So this would cancel that whole group there. So I would have x times y minus 3 equals y plus 2 now. I'm going to go ahead and distribute this on the left side. So I have x times y minus 3x equals y plus 2. I do want to solve for y. So what I'm going to do is I'm going to move everything with a y to the left side and everything without a y to the right side, just so I can start organizing myself a little bit here. So this one's going to come over here, and then that 3x is going to go on the other side. So I have xy minus y on the left, and then 3x plus 2 on the right. Now, this one's a little tricky. These are like terms, so they both have y's in them, but we can't really combine them in our usual way. Do note that there is a 1 here. And what I'm going to do, so here's a little trick if you have kind of the same variable that you want to put together, but they don't quite mesh because, you know, here's an x and here's a 1. I can't really add those two things. And you can use your factoring here. So we're going to factor the y out, and I have x minus 1 now. Now what I can do is I can divide both sides by this x minus 1. And I have that y is equal to 3x plus 2 over x minus 1. Okay, so this is a function. And what we're going to do here is just rewrite this. So f inverse of x is equal to 3x plus 2 over x minus 1. Now, it doesn't mention it here, but you do still want to watch out for your domain. Notice that your denominator here, if it was a 1, it would make the denominator 0 here. So you do want to watch out for this. Your book doesn't really do this one, but just a little side note, x cannot be 1 here because 1 minus 1 would be 0. You make that denominator 0. So just a little note that you still do have to check domains a lot of times for these inverses. All right, and we'll do one more. So I'm going to rewrite it as y equals x squared. And then I'm going to go ahead and swap those x and y's. So I have x equals y squared. And then our third step is to go ahead and solve. So remember, if you just have a y squared, we can use that square root property. But when you have squares or fourth roots or anything like that, you have to take plus or minus the square root. So you end up with y equals plus or minus root x. Now, plus or minus is an issue here because it's not a function. We get two answers out for the same x value that we plug in, right? So for instance, if x was 4, then you would have positive root 4, which is 2, and you have negative root 4, which is negative 2. So this is not a function. So there is no inverse function here. And you're going to see that plus or minus idea anytime you have an even power on the y. So watch out for even powers on the y when you solve. Now it's the y after you switch, right? So once you switch and you're solving, then you're watching out for those even powers on the y. I will note that we can sometimes put a restriction on our functions that don't have inverses. So for instance, something like this, we will often look at maybe just half the graph. So we may only look at x values that are greater than or equal to 0. And then what happens there is because we restrict the original function, we're able to then find an inverse for that part of that original function. So you may see that sometimes too. So don't assume that anytime you see an x squared, it's always not an inverse. It depends if there's a restriction or not. If there's no restriction, so here there's no restriction, then it doesn't have an inverse. But if we're able to restrict it sometimes, you do want to go through the process and check to see if you still get that plus or minus idea.